Yeah, we have around 35. Yeah, I think we can start. Yeah.
Oh. Okay. Good evening, Professor Arindam Ghosh, Professor, Department of Physics, Indian Institute of Science, Bengaluru, and today's distinguished speaker, Professor Anindya Das, convener of Bangalore India Nanotalks 2022, and Associate Professor, Department of Physics, IAC, and Shri A.B. Basavaraju, Director Technical, and Managing Director KSTePS, Department of Electronics, IT, BT, and Science and Technology, and all the distinguished participants. It's my great pleasure and honor to welcome you all for today's Nano Talk. To engage the Nano community throughout the year, the Bangalore India Nano monthly webinar series is being organized since last month as a platform to reach out to a larger audience, including younger generations from universities and colleges, and keep them connected to the Bangalore India Nano, which is a flagship event since 2007. This program has been initiated at the suggestion of Vision Group on Nanotechnology under the chairmanship of Professor Navkant Bhatt, Chairman, Vision Group on Nanotechnology, and Dean, Division of Interdisciplinary Sciences, Indian Institute of Science. This webinar is also mentored by Professor Ajay Kesu, FRS, the Principal Scientific Advisor to the Government of India and Distinguished Year of Science Professor, Department of Physics, IAC, and member VGND, Government of Karnataka. Now I request Professor Anindya Das, convener of Bangalore India Nano Talks 2022, to introduce today's distinguished speaker. Sir, please.
Yeah. Thank you, Dr. Venkatesh. Good evening to everyone, and welcome you all to Bangalore and India Nano Monthly Webinar Series 2022. This is our second talk. We started in July last month. And this program is an initiative under the Karnataka Science and Technology Promotion Society, and particularly the Vision Group on Nanotechnology of Government of Karnataka. The main purpose of this webinar series is to basically to give a platform to connect a broader audience, a larger audience, mostly the younger generation from university and colleges, so that they are connected to this Bangalore Indian Nano brand. So that is the main purpose. And so with this, let me introduce today's distinguished speaker. And it's my great pleasure to introduce today's speaker, Professor Arindam Ghosh, eminent and renowned physicist, scientist, writer, and speaker, as well as teacher. Professor Ghosh, currently at Department of Physics, Indian Institute of Science, Bangalore. Professor Ghosh doesn't need any formal kind of introduction. He is very well known internationally, as well as, of course, in the various field of nanoscience and nanotechnology. I briefly mention his contribution and achievements. Professor Ghosh research interest in the area of understanding physics, as well as the device perspective in various kind of two-dimensional materials, in particular to detect ultra-sensitive optical signal, designing and tunability of thermoelectric devices, and very recently efficient memory devices and so on. And he has been key members of several international and national boards. For example, he is the leader of National Mission of Quantum Technology, as well as Quantum Initiative at Indian Institute of Science, Bangalore. And Professor Ghosh has guided more than 20 PhD students so far. He has been a member of many editorial board of many prestigious international journals. He has been recipient of many international and national prestigious awards. So just to name few of them: prestigious Swarna Jayanti Fellowship, prestigious Shanti Swarup Bhatnagar Prize, in the US Science and Technology, Oxford Instrument Young Nanoscientist Award, PK Iyengar Memorial Award, J.C. Bose National Fellowship, as well as very recently 2020 Infosys Prize. I will not take any more time. I think audience is eagerly waiting for this talk. With this, I'll hand over to Arindam. Arindam, the talk is 45 minutes, and the remaining time is basically question and answer. I'll request the audience, if you have a very short question, you can unmute and you can directly ask the questions. But if you have a longer question, please wait until the end of this talk, and then we'll address during the discussion session. Yes, with this, Arindam.
Thank you, sir.
Okay, thank you. Anindam, can you hear me?
Yes, sir.
Absolutely fine. Yeah.
Okay, wonderful. All right, thank you very much for the kind introduction. I would like to thank Anindam and Mr. Vasabraju for giving me this opportunity to come to this very important forum to reach out to a larger audience in Karnataka on the nano aspects. And I know, this is something which we have been doing, and it's an excellent initiative. And I'm quite sure that this is going to benefit a large number of students as well as, professionals in the field, and motivate them to do this kind of work, which is gaining momentum every day. It's becoming a global phenomenon, and how this whole field is moving. And what I'm going to do today is we'll try to capture a small aspect of this and try to show where we are taking this nano, and in the domain of nano, the 2D in particular, not from just starting from the basic scientific aspects to technology, which eventually will hopefully impact our lives in a very critical way. So today's talk will be on science and technology with atomic layers. And obviously, this is going to be a broad talk. So I'm going to start asking the question, what are atomic layers? Okay. It's something which there's a reason why I showed a pencil, because the atomic layers come from the heart of the pencil, which is at the tip, or which usually contains a material which we call graphite. It's this large chunk of black colored material, which essentially got the whole field of 2D material started nearly 17 years ago. But before I go there, just for students, the graphite is essentially a crystal, and it's a crystal of a large number of layers of hexagonally oriented carbon atoms. Okay. So this is a typical crystal structure of graphite. Each carbon atom have got 4 bonds, and there are 3 which are in plane and 1 which is out of plane, called the PZ orbital. And then each atom is very strongly connected through what you call sp2 hybridization with the neighboring carbon atoms. And the one atom, the one electron, which is PZ electron, that essentially can move around and gives it electrical conductivity. Now it turns out that individual layers of this 3-dimensional material is called graphene, and that graphene is the most important component of the 2D material, which got just a second. Let me put it in the pointer mode. Yeah. So because of this layered structure, you have layers of hexagonal 2-dimensional lattices. What happens is the layer interaction between the 2 layers are extremely weak compared to a solid that you take in 3-dimensional solid, which are covalently bonded or ionically bonded. For example, these 2 layers are usually bound with a very weak force called a van der Waals force. And if you compare the force between 2 successive layers, you'll see that typically the 2 layers in graphene is about 1,000 times or lower than usually covalent bonding or ionic bonding. For example, simple salt, the sodium chloride that we take in our food, the kind of interatomic strengths or force is more than 1,000 times or nearly 1,000 times that of graphene. Okay? So this is an important property which allows us to separate a single layer of these carbon atoms from the rest of the bulk solid. And this is why a 2-dimensional atomic layer can be formed by taking out one layer out of this billions of layers in the graphite. Okay, so this is what is called an atomic layer. Now, it's not as easy, obviously, as I say, because when it was done nearly 17, 18 years ago, in a paper which was published in Science in 2004, 22nd October issue, it made a massive impact, a lot of interest all over the world, that at last layers or individual or very, very thin layers of graphene has been separated from the graphite crystal. The paper now has been cited more than 66,000 times, which shows the importance and the impact that this work had on the scientific community, and not just then, but it continues in equally or faster at the, 18 years have just gone by. The two lead authors, the Kostianov and Andrei, they eventually got Nobel Prize for this isolation or successful isolation of graphene from graphite in 2010. The interesting part is the way they did it, simply because this was an extremely easy and something that can be tried even in schools and colleges of separating graphene out of graphite. It's very simple. What they did, they took a layer, or they took a substrate, which is of silicon, and then oxidized, the top surface is oxidized, making it silicon oxide. And then they used a simple tape. You have the sellotapes at home, and put graphite on that, and then you press it on the silicon oxide surface, and then discard the tape. What turns out that it leaves graphite or graphene, an individual layers of graphene, with some probability on the surface, and then they put electrical contacts and leading to a field effect transistor, which led to a lot of very interesting electrical properties. So this was the start of graphene that we think in the modern day research. But the story of graphene actually started much earlier. The fact that graphene is a very interesting element. It started nearly, in 1947, 75 years ago, when Philip Wallace, who was in Canada, a theorist, was calculating how the electrons in graphene, the move and their energy in a lattice of hexagonal carbon atoms. What he was trying to do, simply, he was trying to calculate the energy and the quantum mechanical properties of electrons, which are bound to these atoms on an hexagonal lattice of graphene, something like this. Okay, and he used a method called the tight binding model to understand or calculate the energy. What he found is something very interesting. He found that the energy of electrons in this, is there a question?
No, there was a audio was not coming, but now it's okay. Yeah.
Okay. All right, so I'll continue. Okay. You can hear me now, right, Arindam?
Now perfectly fine. Yeah, please.
Okay, good. So what Philip Wallace calculated way back in 1947 is that there is a cone, or what is called a Dirac cone, along which the energy of graphene depends on its momentum. K is like a momentum, and E is the energy of graphene. And secondly, it's like a semi-metal in which the electrons are completely filled in the yellow part of the cone and completely empty in the upper part of the cone, which is called a conduction band. So it's like a zero band gap material where the conduction band and the valence band come together and meet at one particular point. And this point is called Dirac point. So this was a unique aspect of graphene, which is very dissimilar or very different from conventional semiconductor and metals, etc., where electrons have mass, whereas in graphene, electrons behave as if they're like photons, where the energy of the photon is also directly proportional to the momentum of the photon. In that sense, electrons in graphene behave as if they're like photons, although their velocity is much, much smaller. So this conical band structure was the starting point of a large number of applications for graphene. And I'm going to give you a couple of very interesting examples in this talk to tell you that this uniqueness eventually started the field and how we have expanded and propagated through it. So because of this conical band structure, the electrons in graphene can move really, really fast. And that gave rise to a very interesting electrical transistor, a field effect transistor, which is there at the heart of all our electronic devices, where you have charges moving from one side to the other of a device, which you modulate by applying an external electric field called a gate. So this is a typical field effect device where you have a source where the electrons come in and a drain where it goes out. And then you have got a gate, which is an external body which applies a potential on these electrons, which is moving from one side to the other. Okay, so this is a basic elementary foundational structure of a field effect transistor. Now, what the original discoverer of graphene did, they used graphene exactly in the same manner, in which they created an oxide, which is like this, which is silicon oxide, and then they put a doped silicon, which is like a metallic gate, and then they put electrical leads to act as source and the drain. And then you apply gate voltage, which changes the electron density in this channel, and that changes the current or the resistance of this channel of graphene. Okay, so this was the original device structure that was made with graphene way back in 2004. What was found is very interesting. That in case of graphene, you can see that as you increase the electron density by applying a positive gate voltage, you get conductivity to increase. Again, that can be understood because you are doping graphene the way you dope any semiconductor. You dope graphene with electrons, and hence the electrical conductivity is increasing. If you put negative gate voltage, now you are inducing holes in graphene, and hence the electrical conductivity is going up again. So this is the hole doped regime of graphene. Now I have put two different lines, which I'm going to clarify later. That one is red, other is black. And it turns out that one is on silicon oxide, which is like this, which is usually a very dirty amorphous substrate, whereas the red one is when you keep the graphene on a very clean single crystalline substrate. That time you get a much larger electrical conductivity. The reason behind it is that the electrical conductivity is directly proportional to what you called electrical mobility of any charge carrying system. Sigma is equal to the electronic charge multiplied by the density of carriers multiplied by the mobility of the carriers. And the mobility tells you how fast a charge moves from one end of the sample to the other. Now, it turns out that if you look at the slope of the sigma versus density, you get the calculation estimate of the mobility. So when we do that, the number that comes out, even on silicon oxide, the mobility of charge in graphene is in the order of 1,000 to 10,000 roughly. Whereas if you put it on the single crystal substrates, very nice quality substrates, which have got no impurities, etc., then this number can be much, much larger, up to 1,000,000 centimeters per volt second. Now, this is an extremely interesting and important observation, because this is much larger than conventional transistors that we find in our electronic devices made from silicon, for example. Okay, so this is why originally graphene was immediately suggested when it was discovered and its electrical property was measured. Then it was suggested it would be wonderful to make high frequency fast transistors. Now, as indeed the case, actually, if you take a look at the current state of the art of electronic industry, where the high-speed electron RF devices are always sought after, because you would like to have the mobile phones, the computers work faster, then you need high-frequency RF quality devices. And you can see graphene is at present, even current experimentally, at a given channel length, you see how fast an RF device will work will depend how long the electrons have to travel from one end of the sample to the other end. And that is given by what you call the gate length. Okay, LG is the gate length. Typically, LG in the current state-of-the-art devices is in the order of 5 nanometer. Okay, whereas if I take a typical graphene, typical field effect device with gate length, you can see the speed at which a device works increases as the gate length is decreased. Okay, and this is called a frequency scale is called FT, which tells you how fast you can operate the device. In the case of graphene, at around 100 nanometer of gate length, you can see it is the fastest known transistor of about 300 gigahertz. Theoretically, this should be in the order of a terahertz or 1.4 terahertz, but that has not been achieved so far. So this is one aspect of the unique electrical property of graphene. But I'm going to show you some other interesting property which comes out from its unique conical band structure. And I'll tell you the application of that. And for example, it happens in a battlefield, for example. What will you do with graphene? We can do something unique that many of the other property materials simply cannot do. So, what happens is that when we are at room temperature, our body is roughly at 300 Kelvin, right? And if you have this red curve is at 300 Kelvin, okay? When we are at these temperatures, we are like a black body cavity in which we continuously emit photons. And these photons have got a rough energy of 0.1 electron volt or 100 milli electron volt or so. Now, what happens is that when we wear clothing, these photons continuously get absorbed by our clothing, and then it gets re-emitted. And when we are even in the dark, a thermal camera can actually record these 100 milli electron volt energies, and they can image us. And you can see the image here is essentially a soldier who has been imaged in the night vision camera or infrared camera, which can record these kind of radiations at 10 micrometer wavelength. Now, can one do something else that these radiations at these 10 micrometer wavelengths can no longer get transmitted but reflected back to the body? And this is how graphene can probably be of help. For example, if I take graphene, what happens is when I shine these waves of 10 micrometer wavelength, the electrons from the valence band gets transferred to the conduction band, and it gets absorbed in graphene, and then graphene re-emits that wavelength, and that goes to the camera, and you can get imaged. However, if I dope the graphene the way I doped earlier, you saw the way electrons and holes were being doped using a gate. If I dope graphene such that there is no available state at these energies of few hundred milli-electron volt or so, this is then a charge from here cannot get transferred to a fill state through a phenomenon called Pauli blocking, and hence the energy that was coming that can no longer get absorbed, and if they cannot get absorbed, they cannot get emitted either. And this is how a ghost suit can be created. You can see this has now been demonstrated very nicely. You can see this is a human hand, the thermal imaging of a human hand, and this is a graphene sheet that is sitting without any doping, and you can still see the image of the hand through the graphene. But if I now dope it using graphene, using electrostatically or using chemically, then you can see now the hand can no longer be seen, and it has disappeared, it has vanished. That's because the infrared radiation that is emitted by the body can no longer penetrate through graphene and get re-emitted. So this is how graphene can be used for adaptive camouflage. And this is some interesting application of this unique band structure. So I wanted to give you this example. So since then, we have understood a large number of different properties of graphene. For example, I already told you about its unique field effect transistor properties. can be fast switches, it can be foldable electronics, papers, etc. There has been a lot of research going on in that direction. It has got huge thermal conductivity and hence high and also very high Seebeck coefficient. So if you want to create now composites which are thermally conducting made of plastic, then you can use graphene as a very interesting, important pillar in the composites. Then you can have a very large surface area of nearly 2,600 square meter per gram of graphene, which is because it is highly conductive. It has got a very interesting application in supercapacitors, in car battery, for example, and many such battery applications or energy storage applications. Now, because of the unique mechanical property also, because graphene has got a breaking strength of 42 nanonewton per meter, which is nearly 100 times larger than the equivalent thickness of steel. So it can be in terms of very strong applications in ballistics, in concrete, for example, in the light and strong composites. We have nearly 98% transparency, so you can use it in a solar panel, in light modulators, and also, because graphene has got a beautiful crystal lattice of carbon atoms, it doesn't allow gas or water to flow through. So if you want to non-porous structural or composites, then graphene is a fantastic pillar to work with. Waterproofing is another example. For example, if you put graphene in concrete, then it has been shown that its strength can be increased by at least a factor of 200%, and it can be 4 times more water resistant. Imagine your building having graphene as a pillar, its lifetime is enhanced by a significant amount of time. So graphene is something which is very interesting, and since 2004, people started looking at all sorts of different properties. While this was going on, there was another bunch of scientists working at EPFL in Lausanne in Switzerland, who suddenly came up with a very interesting analog of graphene called the molybdenum disulfide. Okay, so molybdenum disulfide works exactly the same way in terms of the way graphene was synthesized and put on a substrate. It was done exactly the same manner, taking a mechanical scotch tape and then put it on a substrate. Just to give you a little bit of understanding, molybdenum disulfide is also a hexagonal crystal lattice. Here you can see molybdenum and this sulfur from the view from the top, and in a crystal structure called trigonal prismatic crystal structure. This is what a naturally occurring molybdenum disulfide is. But there's a crucial difference between graphene and molybdenum disulfide, because molybdenum disulfide is not a gapless or zero band gap semiconductor, but it's a real semiconductor with a direct energy gap. So there is a 1.9 electron volt energy gap in molybdenum disulfide. That was great, because now you can have a silicon analog, which is much thinner than the silicon itself. It is just about 0.5 nanometer, 0.3 nanometer thick system now, as opposed to silicon, which is the silicon inversion layer, which is about 0.2 nanometer in thickness. So this immediately people wanted to see if this can show exactly the same kind of field effect transistor properties that has been observed in case of silicon. The answer to that question was yes. You can see that as you decrease the gate voltage to negative values, then the conductance through this source and drain contact goes to 0. And when you increase the gate voltage, the conductance goes to very large number of nearly on-off ratio. This is on, this is off. This leads to nearly 10 to the power 5, 10 to the 7, with a mobility of about a few hundred centimeters square per volt second, which is very similar, if not slightly better, than typical silicon MOSFET that you get in the market today. But more importantly, there was something else that turned out. Very next year, 2011, the Nature paper came out. 2012, people found, because of the band gap that is available in molybdenum disulfide, you get a transistor that is sensitive to light. So you can see the red one was when you shine light on molybdenum disulfide, and the black one is in dark. So this essentially starts the era of two-dimensional optoelectronics way back in 2011. But optoelectronics means that now you can convert light into electricity by these two-dimensional materials or two-dimensional surface semiconductors. After this, there's a series of work that has been done. There's a large number of materials which have been developed, which cover the electronic band gap from ultraviolet range to the microwave range. So this application or coupling of light and electricity is one of the major directions of research and development using two-dimensional materials. Okay. To look at the beyond electronics, right now, the 2D material and community is looking at a large number of applications. As I told you earlier, in the case of sensing, medical, looking at the sensing of breast cancer, where the binding of the proteins with the two-dimensional materials can be taken. In quantum technologies, you are looking at emission of single photons. In neuromorphic computing, you are using these systems as memory devices, which I'm giving you a small example a little bit later. So there's a very large number of applications, and now it has been put in the roadmap for semiconductor heterogeneous integration processing line by IMEC and several other big electronic warehouses. Okay, so we have now about 330 to 40 known two-dimensional systems, starting from graphene in 2004 to layered chalcogenides to even oxides. There are about 30 to 40 known, and we are continuously evolving. These are all materials which could be separated out using Scotch tubes. However, calculation shows that there could be more than 1,800 possible such compounds. So that's great. It's something which is a lot of material to play with and look at their physical properties. Now let's come back a little bit, and I'll give you a little historical perspective. So you see, what was happening in University of Manchester in 2004, that started with graphene. We looked at molybdenum disulfide came in 2011 from EPFL in Lausanne. What we have been doing around that time at Bangalore, we were trying to get these two together. That is graphene and take a molybdenum disulfide. And we were trying to put them on a chip and try to understand what happens if you put these two completely separate, independent material together. Do we get something a little different? Turns out that yes, we were not only the first to put them together, but we also showed for the first time that how making two different chemical genre of two-dimensional materials, when they come together, they lead to what you call emergent properties. An emergent property is a property that in a hybrid system that does not exist in its original counterparts. What I'm going to show you in a couple of minutes or so, that how putting graphene and molybdenum disulfide put together leads to a property that was not present either in graphene or in molybdenum disulfide. And that led to a lot of study or a lot of activities in what you call today designing material on a chip. So in order to put this together, we have what you call a new direction of material synthesis called van der Waals heterostructures. Okay. Essentially what you do today is we can make materials by putting them on top of each other, in which you take, say, and you can put them in sequences that you want. For example, here we are putting a layer of graphene on a layer of boron nitride. The whole thing is put on a bilayer graphene, and then the whole thing is put on a molybdenum disulfide layer, giving rise to some structure which is called a van der Waals heterostructure. Now, if you ask me what exactly is this, it's essentially a user-defined material which doesn't exist in nature, something like this. You take a body of a tortoise and a head of a crane, and you make together something completely different. Of course, you have to ask the question, is it something useful or not? And I'm going to prove to you that it is something useful to do, or something like a giraffe and an insect. Okay, so this is exactly what we are trying to do. We are trying to mix and match, take materials from different genre and put them together. And all these can be done with a simple microscope. Okay, so for example, you can make two-dimensional stacks of like this graphene on just 2 layers. We can make 3-layer stack, we can make 4 layers, 5 layers. We can make a large number of different stacks now in the laboratory using different materials and different orientations. And these have got extremely good quality, interface. There's no doubt this atomically clean interface leads to very interesting new physics. But as I said, van der Waals heterostructures were there before we started, but at that point of time, people were using it for improving the quality of the material. For example, by putting graphene between 2 layers of boron nitride, a very high mobility was obtained, as I showed you earlier. But what we did for the first time, we put, as I said, graphene on molybdenum disulfide. That led to a new kind of optoelectronic transistor. And what we did is we put the graphene on molybdenum disulfide and put electrical conduction and something similar to this. What you see is something very interesting. Whenever you switch the light on this layer, the current through graphene, which is sitting on molybdenum disulfide, jumps dramatically by a very large number. And you can go on in cycles, and then you can see every time there is current, there is light, there is a change in current. And this current is called photocurrent. And a figure of merit in any optoelectronic element is how much photocurrent you get for a given power of light. And it turns out that this number called photoresponsivity is nearly 10 to the power of 10, which is 10 orders of magnitude larger than conventional intrinsic photoresponse in bulk semiconductors like silicon, germanium, and semiconductors like that. So this essentially led to a very interesting new set of devices. If you compare the graphene molybdenum disulfide hybrids compared to standard silicon detectors, the responsivity is nearly 10 orders of magnitude larger. You can see this is about 1 ampere per watt. This is about 10 to the power of 9 to 10 ampere per watt, which if you can detect 1 nanoampere in your laboratory, it leads to an energy sensitivity of nearly 10 to the power of minus 19 watt. So at 10 to the power of minus 19 watt, we produce nearly a measurable of 1 nanoampere of current. You know how much is 10 to the power of minus 19 watt? It's essentially a candle on surface that can be detected 120,000 kilometers away with a 1 square meter area. So that is the amount of power that goes through the 10 to the power of minus 19 watt. It's extremely sensitive photodetector that can be created. You see, neither graphene nor molybdenum disulfide are such sensitive detectors. We could get this detector because we have now mixed and merged 2 different elements and pulled out the best of these 2. Here what happens is that light comes, it forms an electron-hole pair in the molybdenum disulfide layer. The electron then goes in graphene and it moves around, and it gives you a large optical gain, which leads to an extremely high sensitivity to optics. Of course, later we use this, you made various electronic devices like a single photon detectors and a memory device in which you use pulse of light to write and a gate voltage to erase, and you can go on for on and on as an optoelectronic memory, or very sensitive optoelectronic memory. So I'm going to give you an example of how a 2-dimensional materials can be used for such kind of purposes. We are not the only one. After we started with this direction, there are a series of groups from all over the world made new type of devices like light emitting devices, photoelectronic devices, and this field continues to grow with new materials coming in, and such device architectures are being discovered every day. So I'm going to give you another small example. I gave you the example of how such optoelectronic structures give you optoelectronic sensitivity. I'm going to take you a completely different domain and show you how such devices can aid in mimicking the activities of brain, what you call a neuromorphic device. To understand that a little bit, I will tell you how 2 neurons in our brain communicate with each other, how we train. What happens is that when we train a neuron and when we transfer information through our neurons, for example, through a synapse, which is the junction between two neurons through dendrites, we have a region which can either be electrically conductive or electrically insulating. If a material is, if the two neurons are transmitting information correctly, we want to make sure that their electrical conductivity is large. And if they do not, then you would like to make sure that the synapse is inactive, and you reduce the electrical conductivity of that junction. In order to do that, you need to create a memory in which you keep on giving positive pulses, which is called potentiation. And the more the number of pulses through this junction, you would like to create the neuron to have high conductivity. And if you want to deactivate the neuron, then you keep on putting negative pulses. And this is a mechanism called depression, in which the electrons essentially the conductivity goes down, and the synapse becomes electrically non-conducting or deactivated. Now, this is something which is how our brain trains a large number. We have got billions and billions of neurons in our brain, and each junction is trained whether the junction is going to transmit information or not. At the end of the day, the brain also works through electrical pulses. Of course, not electrostatic pulses, but using electronic, chemical, through chemical means, it transmits pulse from one neuron, the presynaptic neuron, to the postsynaptic neurons. So question is, can we make a memory in which then if we keep on giving pulses using a gate, and we change the resistive state of a device? And this is something which we did nearly 2 years ago. And we created a device in which a molybdenum disulfide layer is our channel. We have a layer of boron nitride and a layer of graphene, which acted as an electron storage layer. What you do is that you give pulses to the gate underneath, and that positive pulses stores charge in such a way that it makes the channel over here conducting. And if you give opposite negative pulses here, then the charge essentially gets washed away, and the molybdenum disulfide layer becomes insulating. So this is the potentiation cycles and the depression cycles. So you can see this is the large number of pulses that we have been able to give to the silicon gate. In some pulses, you can see with every pulse, each red dot is a pulse on the gate. You can see the electrical conductivity increases, and then we give pulse in the opposite direction, and electrical conductivity comes down, and the depression cycle. What is interesting about these, by using 2D material as a platform for such devices, you can see that energy dissipation per pulse is extremely low in this molybdenum disulfide layer-based memory device, even lower than the kind of energy that human brain uses. Right, so what I did in the last 30 odd minutes is that I gave you a little bit of understanding about how different applications in 2D individually of the hybrid structure in a diversity of fields, from electronics to optoelectronics to neuromorphics, and there are many others which I simply don't have time to say here. What I'll do in the next 5-7 minutes that is left in this talk, I will give you a perspective of the technology. 2D materials have crossed 18 years now, and there's a huge drive now to take 2D materials to the market. What I'll do is that I'll give you a little bit of understanding, a perspective of where we are in terms of technology, based on all the science that we have been doing in our laboratories today. So this is what is technology with 2D layers. And first technology is electronics technology. If you look at the presentation that I made today, the first aspect of it, or our overwhelmingly stressed aspect of it, is electronics, because that is what my group also works on here. And in order to get to electronics, we have to create large area of two-dimensional materials. And there are now several techniques. Epitaxial growth at the wafer scale of two-dimensional materials, which can come on silicon carbide or molecular beam epitaxy, is one aspect of making them in wafer scale. Or chemical vapor deposition is also an extremely important and probably a more promising way of getting two-dimensional materials on variety of substrates. Not just graphene, which you see here, but also the transition metal dichalcogenides, which are grown using several techniques, bottom-up techniques of molybdenum molecular epitaxy, then pulse laser deposition, spray pyrolysis. But chemical vapor deposition is one of the most important areas of growing these on sapphire, silicon oxide, and several substrates. We now have 6-inch wafer scale growth of high quality molybdenum disulfide, tungsten diselenide, tungsten disulfide layers, single layer over the entire wafer that can now go to technology. So that's very good. So where are we with the technology? So by 2018, by around early this century, in the first decade of the century, the standard Moore's law scaling was almost over. Essentially, since 2005-6 onwards to 28 is now what we are calling this as a material-based scaling era, in which you are no longer making the silicon in our devices anymore smaller, but you are looking at copper instead of aluminium in interconnects. We are putting high-K dielectric in semiconductors. We are using FinFET kind of alternative architectures to make our electronic devices more efficient, smaller, etc. Now, this is going to stop. There is a limit to this. And what is going to happen, and now it's already happening as I give you examples, it's an era of heterogeneous integration, or more than more. It's a Moore's law of doubling the number of lattice every couple of years is no longer tenable with pure silicon. Now, if you want to go there, you need to now start taking help from other materials. And in this context, two-dimensional material is one of the most, if not the most promising material that we have today. And the way in the processing line, 2D material coming in is, it's coming in as back of the line switches, because you can use P-type switches or P and N-type on the same material. So there are now these kind of applications through heterogeneous integration of silicon processor and two-dimensional materials that's happening in various electronic manufacturing units. In the next 4 years or so, we are going to end into CMOS plus X era. In this era, we are going to talk about van der Waals heterostructures, the kind of FETs that I'm going to talk about, to perform certain key properties that is beyond silicon CMOS today. And these are in high performance computing. I don't think this is very clear. I don't know whether it's very clear, but you'll see the energy. This is the energy of a 32-bit adder that we need to achieve by the year 2028, in which the typical numbers can be achieved only when you integrate silicon with two-dimensional material-based field effector devices. So it's an extension of performance of CMOS with silicon, and that is why this era will be called a CMOS plus X era, or could be called. In addition to that, photonic integrated circuits, intercommunications will, again, silicon will start coming in with two-dimensional materials on a single integrated chip. Sensing and health monitoring devices, which are also based on silicon, will come with two-dimensional material as an additional part. And then finally, 2030 onwards, we are talking about beyond silicon CMOS scaling altogether. Silicon is simply becoming untenable, and the Internet of Things, quantum technologies, neuromorphic computings will be based on two-dimensional materials and ultra-thin, atomically thin electronic industry. So this is roughly the electronic timeline, devices based, which are electronic devices with two-dimensional materials, essentially taking over silicon era and going into a completely different era. And this last 26 onwards, one is talking about what you call a more era in silicon, in international technology roadmap. Okay, so this is one direction. This is one direction of electronic computing. The second one is the bulk application that I was talking about. How is two-dimensional materials going to come in our lives in other than electronic applications? In energy, you can have the wind turbines as fillers in the wind turbine oil. to get a very nice long-lived turbines so that their efficiency doesn't go down, with smart textiles, aviation as low weight, high strength composites, in concretes, in flexible electronics, in food packaging. There's a huge amount of possible applications that has already been demonstrated in the laboratories. The question is that how do we achieve that? Achieving that requires large-scale manufacturing of two-dimensional materials. And the most promising in that is what you call the liquid phase exfoliation. And in that, there are 2 or 3 different directions. One is you can put intercalate heavy atoms in two-dimensional materials, then you exfoliate, and they fall apart. This is the way, which was very old way, you make scrolls of two-dimensional materials, some of them. The graphene oxide or graphite oxide through Hammer's method, it increases the distance between layers and then you exfoliate them. One of the most popular ways of low-cost graphene over a very large yield is one of the most important directions today. And the third one is using bulk and solvent. You put the 2D layers in solvent and with a similar kind of surface energy, and you exfoliate them and you get nanosheets. So these are the currently adopted area of two-dimensional material generation. Anindam, can I take 4 more minutes, 3 more minutes? Is that
absolutely, okay? Absolutely, yeah.
Okay. Now, there are problems. The problem is the prohibitively expensive. So if you look at the typical cost of these kind of two-dimensional materials today, and you make these available for all the technologies in which they can make a real impact, is not commercially viable simply because you can see to produce gram scale of two-dimensional materials, you have to pay few dollars to hundreds of dollars, depends on what's the quality of such two-dimensional materials. This is graphene, boron nitride, similar kind of cases for other materials like molybdenum disulfide and so on and so forth. So the market need today is a massive increase in production volume at high efficiency and low environmental footprint, because you don't want a large number of chemicals that's going on. So today, in order to make real impact, let's try to look at what is the current state of the technology for bulk applications of two-dimensional materials. And there are 4 different aspects: the production, the quality and standards, cost and pricing, and the applications. Okay. So the production is what we are globally today. In large number of countries, we can produce about 2.5 kiloton or 2,500 tons a year of two-dimensional materials today. Do we have the capability or the capacity? There is a large number of them distributed from all different countries like China, America, Europe, in India as well. In the next few years, it needs to be diversified. These are primarily, the production is primarily of graphene or graphite, RGO, the reduced graphene oxide, but the very little in terms of other two-dimensional materials. And then by the time 2030-ish, we are talking about bulk production of functionalized with two-dimensional materials. The problem is we have capacity, but we don't have demands, because the technology where we would like to implement these are still under development. So the demand today is about 300 to 400 tons per year, and then it's going to go up probably around 2028, 29, we are going to have the demand which is going to be exceeding the capacity somewhere around 10 kiloton a year. But as demand goes, as the quantity of material grows, one needs to have the enforced standard. It is still not there. There needs to be a uniform enforcement of standard, both in quality of the material and the characterization of those materials. The characterization techniques that needs to be standardized across the board from different suppliers. At this point of time, there's far too many suppliers with low and unreliable quality of two-dimensional materials. What about the cost? Where are we looking at the cost of these materials? We are talking about the GNPs, the graphene nanoplatelets, available at around $30 per kilo. Today, we are talking that to be going down to about a factor of 3 when the production volume is about 1,000 ton a year. One expects that number to go down to about $10 per kilo or something like that. So which are the application areas where the businesses are going to come up? You can see there are several possibilities. I showed this. Almost all technological sectors can be affected by a large availability of large quantity of high quality graphene. Automotive, tire parts, for example, printable electronics are already there in a commercial manner. We have essentially polymers and elastomers. We have anode materials and battery, where the battery demands will be 1 terawatt per hour per year, and that's going to happen when our production capacity will become approximately 100,000 to 1 million ton a year. So this is a huge scope of innovation and market opportunity that happens today. This is our own company, which essentially looks at production of our production of boron nitride. For example, we are now able to create boron nitride at twice the state of the art at much lower, shorter time scale. And we are certainly not the one. There are more than 150 startups that are now getting into the market to create graphene and other two-dimensional materials in a meaningful, economical, and efficient manner. So I would like to stop here. This is my summary. 2D material is ready to impact several frontiers of technology, even as its science evolves. There are new applications, new areas where it's being implemented, and new science, new discoveries are taking place, but it's already there, ready to make technological impact. The interesting component here are two. One is it's not only increasing improving performance of existing technology, but it is also leading to innovation and new disruptive functionality in various technologies, and that is one of the main features of this development. And the bulk quality and the large area quality production with low cost, high quality remains the key challenge. I will finish with one statement that started the era of IoT in 2015. Create devices no bigger than a grain of rice that can sense, compute, and communicate without wires or maintenance for 10 years. Now, if you want to have such kind of ambitious goals with electronics and device performance, we got to see beyond silicon. And this is probably where two-dimensional materials will play a major role. Arindam, thank you very much for listening.
Yeah, wonderful talk. Yeah. So it's now open for questions. You can raise your hand or you can unmute and directly ask the speaker. Is there any question?
I have one question. No.
Sure. Yes, Krishna. Yes, please go ahead.
The photo responsivity you talk. So, in which factor the photo responsivity depends? It's only depends on the power of the excitation, or some other factors it depends. And second question is also the response time also depends on what factor?
Okay. So very good question. So photoresponsivity in the kind of charge transfer based devices that I have showed you today is it depends on power inversely proportional to power. That is, responsivity decreases with increasing power, and it becomes extremely high when you go to low power regime, simply because when you keep on increasing the power, a lot of electrons travel from molybdenum disulfide layer to the graphene layer, and then it stops more and more electrons to come in. So that is why the responsivity is much higher at low power, and it decreases with increasing power. As far as the time of response is concerned, this is something which is still an open question, and this is happening in my laboratory now to look at the time speed of these responses. What people have done using pump probe spectroscopy, they looked at the charge transfer speed between two layers, that is graphene and transition metal dichalcogenate layer, And that happens extremely fast at the timescales of few picoseconds. So this is something which would be very interesting if we can achieve this, because that would lead to photoresponse at extremely fast pace. So that's the short answer to your questions, I hope.
Okay, thank you, sir. Okay.
Yeah, Mr. Subhojit, you can
Yeah.
unmute. Yeah.
So thank you, sir, for the nice talk. So I had one question, like, what are your views on like in what aspects these 2D materials will impact directly on quantum computation? Like, do you think they're going to beat the superconducting qubits, like in terms of the occurrence time or something? Sir, yeah.
Okay. Good. There's a lot of work going on in that direction. As far as the two-dimensional material is concerned, I did not give that information. They are important and relevant to all verticals of quantum technologies, not just quantum computation. It's in quantum sensing, quantum metrology, quantum communication. As far as the quantum computation is concerned, there is no independent protocols that based on the two-dimensional materials for quantum computation. But 2D materials can have strong impact in sensing, single photon detection, and hence quantum communication and sensing can get affected. But in addition to that, the defects in 2D materials in tungsten selenide, tungsten disulfide, or boron nitride, they are known to be high quality quantum emitters in which you can get single photon emitted from them. So they can be used in sources, in say photonic processors, in quantum communication protocols, and various other processes. So those are the regions where most of the 2D research is directed in relevance to quantum technologies.
Okay, thank you very much. Yeah.
So there was one question. Somebody, Dr. Prasoon, who has written in the chat box, he said, how to break 2D layers into nanospheres? Is there any technique beyond ball milling or ultrasonication?
There are several techniques. Ultrasonication is what you just said, is the most popular technique as far as reducing the sizes are concerned, reducing from the bulk material into nanosheets. That's what most people today use for large-scale production. But just ball ultrasonication is not enough. If you want to create high efficient yield, large percentage of yield of two-dimensional material, then you need to make some other arrangements. For example, you need to put them in a solvent with similar surface energy, or do some other things. So there are various variations of these techniques, ultrasonication included, that are being pursued at this point of time.
So is there any question for further questions? Please raise your hand or you can unmute. Yeah, yes, Professor. Yeah, Mr. Sasi Kumar. Yeah, please go ahead. Yeah.
Thank you, sir. Thank you very much for the talk, sir. It was a wonderful talk. I come from engineering college where I teach physics to the students. Normally, when we see this so-called your, K-space understanding of the solids and all, understanding this K-space and the energy gap and all is very difficult. So can we have a talk shortly on this, the K-space and theoretical background of this, the energy gap, because the new materials and new materials are being published and experimented out. When you go for theoretical world, when you start doing calculations, like for example density function theory calculations and all, we start to understand this energy gap. So this basic understanding of this energy gap, if one understands, I think people can really get into more and more understanding of this, especially the case-based data,
Yeah.
because it's so much basic that you started off, because he never felt that it's a so advanced topic. So you started off with case-based data, so easy to understand. So students are always getting into this. Okay, we can understand, but almost we are understanding it, but they are feeling a little bit difficult. That is one question. So shortly, if you have, because you are a wonderful teacher, I've heard a lot of lectures from you. Please, I require more and more lectures on this case-based understanding of all these things for the students. Second thing is that all the materials that has been prepared in the lab. The wonderful thing is that shortly you are going into the startups and entrepreneurs. They can become their own entrepreneurs and all these things. So do you have any programs wherein our engineering students can come to your lab and have internship on this one, sir? Because we require the small gap building. There are from rural areas they are coming, and they are very much interested into these 2D materials. They are very much interested, especially electronics and communication engineering department. They are very much going into the direction of this optoelectronics and piezoelectric materials and all. So do you have any opportunities? My two questions, sir. Sorry
Okay.
if I were going off topic.
No, that's okay. I think both topics are very important. Both questions, that issues that you have raised are important. Coming to the first one, yes, of course, there needs to be a tutorial on the basic calculations of how you can take energies from the simple crystal lattice to case-based calculation. This is a topic that we always teach and we learn during our undergraduation, for looking at how a metal and a semiconductor, or one without gap and with gap, come up. And for that, one needs to have a dedicated lecture. You cannot have a general lecture like this to go to the depth of it, but you're absolutely right. One should be able to do that. And there are, I personally, or any of my colleagues, I'm sure, will be very happy to make that sort of a lecture available to you. Coming to the second question about whether the 2D, taking it to the market and understanding the 2D development, R&D as such, there are now several opportunities in terms of entrepreneurial activities, as well as looking at the basic development, in which you see how the 2D materials are created. That is something which is certainly possible, and both in my group, as my department, as well as our Center for Nanosciences, there are several groups who are involved, not just in synthesis and the science, but also the 2D based entrepreneurialism. So certainly, if you get in touch, that could be a possibility as well, making the students sensitized to R&D and taking the R&D into the market. Certainly possible.
Thank you, sir. Thank you very much, sir. Thank you very much.
Yeah, I don't see any. It's just one query. So how many startups do we have in India right now based on 2D materials?
Difficult question. So as of my number is very poor. I mean, we certainly know of one, maybe several now. In 2018, there was just one, and there was about 150 odd in the world. Right now, I don't have the number. I cannot give you a clear number. There would be nearly 5 or 6 at least in various domains, but it could be more.
Oh, good. Wonderful, Arindam. I don't see any more questions. I think, is there any questions? No, I think, yeah, there are many people have written in the chat. Very interesting, very informative talk, and so nice talk. And yes, this is really wonderful, Arindam. Thank you very much.
Thank you.
Let's thank the speaker once again. And
Thank you very much.
Yeah, we'll close this. Yeah, Venkatesh, you want to say something?
Yes, sir. So, good evening to everyone. We wish to express our sincere thanks to Professor Arindam Ghosh, Professor, Department of Physics, IAC, Bengaluru, for today's excellent talk. Thank you very much, sir. I also extend my special thanks to Professor Anindya Das, convener of Bangalore India Nano Talks 2022 and Associate Professor, Department of Physics, for coordinating the question and answer session. I also thank all the participants of this Nano Talk. We look forward to your continued support and participation in the upcoming Bangalore India Nano Talks 2022. Thank you, one and all. Thank you once again, sir.
Thank you. I can
Thank
log
you.
off now.
Bye-bye. Yeah.
Thank you. Bye.
Thank you. Bye-bye.
ಒಂದು 15 ಜನ ಪ್ರೊಫೆಸರ್ಸ್ ಬಂದಿದ್ರು ಸರ್.
ಇದರ